So can everybody see the slide?
Yeah,
And how about the transition?
also yes.
Okay, great. All right, I believe it's time for us to start. Okay, so first, maybe you have noticed a new kind of assignment um, released on Piazza, which requests everybody to send a project proposal. So basically, you need to determine which type of project you want to do for this course. Like as we discussed before, right? We have two types of projects: exploratory or competitive. Right? The competitive project is just some casual competition. The TM has already shared the link with you. So if you want to do that, remember you can you cannot team up for that competitive project. You have to do it by yourself. You just click into that link and then register your account and then fill out the Google spreadsheet shared by TM so that let us know your UID and name and account, right? So we can watch your ranking and scores, all kind of stuff, and give you the grade. And if you want to do exploratory project, meaning that you want to apply machine learning techniques to address any problem or research you want to do, uh, yeah, you should consider what kind of topics you want to do, right? And do you want to team up? You're allowed to have one team member at most, right? And think about what kind of problem, how do you formulate them, and why do you want to use machine learning to address this particular problem, right? Why the traditional approach doesn't work, right? So write a simple, just one page documentation, just describe your team up, your team, your plan, and why you want to do that. Okay, and um, I highly recommend you to start preparing your course project right now, because this project will be carried out along throughout the whole semester. That won't work. Like if you want to do this project in the last 3 days, that's not that's not gonna allow. And we'll have some midterm project report. And also we'll see you have some like at least some dummy submissions by the end of the deadline, and then during the midterm project report, we need to see a few of your submissions and efforts on that. So, but anyway, regarding we have discussed in detail about the project settings and milestones and grading criterion. So you can just look at the course web page. All the details are there, but I just want to remind you to start it as early as possible. Okay. Okay. And any question regarding the course project? Okay, great. So since the last lecture, right? We have not since the last lecture. So by the last lecture, we have finished our first machine learning model, decision tree, right? We know every details to learn decision tree from the data, right? We know the important concepts about overfitting, right? Why overfitting is bad in practice, right? Although ideally, uh, assuming that you don't have noises in data, it is good, right? So, and I believe you have you should have like all the necessary details and techniques to implement your decision trees in your homework one. So if you haven't started doing that, please do it as soon as possible, right? Because deadline is approaching, right? And also it's a good way as the when your mind, like you still have a clear idea about ID3 algorithm, all kinds of algorithms, details and corner and corner cases. It will make you, um, I mean, it will be you will be more effective to start doing that right now. Okay, but today we're gonna talk about computational learning theory. But don't worry, it's just a very brief introduction because this is kind of like fundamental themes to many very important machine learning models and algorithms, as we'll discuss later, like support back machines, perceptrons, all kinds of stuff. So this course is not a theoretical course. That means we're not going in depth about computational learning theory. How do you prove all kinds of theoretical bounds? That's not what we care about. But what we care is the idea, the basic idea of those fundamental concepts. You will see that the definition, the seemingly weird definition of the concepts in computational learning theory is reasonable, especially when we talk about machine learning behaviors. Okay, so our outline is as follows. So we're gonna introduce the general framework and setting for the computational learning theory, and also we introduce several key concepts. So what is the definition of empirical error? What is the definition of the true error, or in other words, generalization error? And what is the goal of developing computational learning theories? So you see that essentially the goal is to use empirical error, which is also referred to as training error, to estimate the generalization error. And then we define, we introduce a very important concept in computational learning theory. It's called PAC learnability, abbreviated for like probably, approximately, correctness. It's kind of weird and lengthy definition, but we'll see what's the meaning. What does it mean later, right? And then we'll try to make some mathematical justification of the principle of Occam's razor, right? We have discussed what is Occam's razor, right? And we say that actually our decision tree learning algorithm ID3 is driven by this principle of Occam's razor. Right? We want to construct a smallest tree which is consistent with the training data, right? But obviously, if you want to find a global minimum tree, it is like NP hard. It's very, very expensive. That's why we use ID3, which is a greedy heuristic. Right? So every time when we find the current optimal feature to split data set, we just fix it. Right? We now backtrack. We're not going to backtrack and re-enumerate all possible features. Right? We just fix all the selected features so far, right? Then we select the best one and to split data set and accordingly, and we expect that we can use a smaller number of splits to arrive the tree leaves such that the whole tree is not too large, right? This is the key idea of the ID3, but it's driven by the principle of Occam's razor, right? So now we want to use this kind of like simple and naive computational learning framework to justify this principle. Okay, so before we move on, let us stand back and look at bigger picture. So this is check one, right? To look at what we have learned so far, right? So we have discussed the general setting of supervised learning, right? So to conduct supervised learning, we need to define instance space, right? So instance space consists of all possible instances which can be used for prediction, right? And label space. Label space consists of all possible labels we can use to predict. Like, for example, your task is to tag the news articles. And obviously, the instance space consists of all possible articles, right? We might have, right? And labels consist of all the interest tags like politics, entertainment, sports, and so on, right? And hypothesis. Hypothesis is actually the function that learned by our learning algorithm. So the supervised learning procedure is conducted in this general procedure, right? We first collect a set of labeled training examples, meaning instances from instance space and their labels generated by some ground truth function, right? And we feed this label data to our learning algorithm. So the learning algorithm can be guided by this training data to search over a range of functions, right? And finally, we're going to pick up a learn function, which is also referred to hypothesis. This is our learning result. And then given new example, we can use our learn hypothesis to make prediction. So this is a protocol of supervised learning. And of course, our main tasks in this semester is to discuss a variety of specific learners, right? For example, we have discussed in detail about decision trees, right? And also we talk about some general machine learning ideas like feature extraction step. Right? And we know that the original instances are usually not, it cannot be dealt with the computer programs because computer programs only recognize binary digits, right? So we need to first extract some kind of high dimensional feature vectors to represent the original instance. And then we'll feed those feature vectors into the learning algorithm. Right? So um, in many practical applications, the feature extraction step is also critical. You'll see that effective feature extraction can lead to superior learning performance. So this is very important. And also, we introduced the concept of overfitting. Right? So overfitting basically means that if you learn a predictor or hypothesis is performing so well in predicting the training examples they use. So in the ideal situation where you don't have any noises, overfitting is not a big issue. Right? Actually, it is good. But if your training data are somewhat corrupted by some random noises, this is it is often happen in practice, right? This is actually inevitable situation. Then if your learning algorithm still tends to overfit data, meaning that you're not only fit the useful information, you also overfit the noises. And the consequence is that those noises can mislead your search over the hypothesis, and very likely it will lead to a bad hypothesis edge that gives you a worse or inferior predictive performance on the future. I'll see examples. We have illustrated this problem by using a synthetic example, right? So later we'll give a more formal definition of overfitting under the uh, framework of the computational learning theory. Okay, so any questions so far? This is just to refresh our mind, right? Um, just to make to ensure that everybody is on the same page. So everybody is good, right? Okay. So now let us talk about computational learning theory, right? So what kind of theoretical, what kind of scenario the computational learning theory cares about, right? So of course, is about all those kind of theories are concerning about the machine learning, right? So basically, we assume that we have a machine learning model which is trained on a fixed set of training examples, and then the model is deployed in the wild, right? Meaning that we just deploy without any restriction, right? So then a key problem regarding machine learning will be how well will your learned model perform on future instances. So this is a so-called generalizability, right, or generalization. So this is some kind of key answer or critical answer the computational learning theory wants to answer. A question the computational learning theory wants to answer. Right? So now we want to give a more formal notations um, about the setup, right? So we define the instance space and denote the instance space by X, and which consists of the set of all possible examples that can be used for training, that can be used for test. And then we define the concept space, C. So what is concept space? It just indicates the type of the target function we want to learn from data. The type or the family of target functions we want to learn from data. For example, um, if our target function is kind of like third order polynomial, right? So then the concept space can be like the family of third order polynomial functions. Right? If your target function, the underlying target function is a quadratic function, then the concept space could be the family of all quadratic functions. So why would we introduce the concept space? It's just to index the type of learning problem. Say if your goal is to learn some kind of quadratic function, well, okay, my concept of space is quadratic function. It might be easier than if when your concept space is a very highly nonlinear, non-convex function set. Right. So a few other concrete examples, like your concept space can be balloon functions, right? We have discussed the balloon functions, right? All balloon functions can be perfectly learned by decision trees, right? Or all n-dimensional linear functions, right? Which we will discuss later. Like we see like linear regression or linear models can perfectly can perfectly learn n-dimensional linear functions. And then from the learning algorithm side, we also introduce hypothesis space, so denoted by this big H. So the hypothesis space just tells you the range of the candidate functions our learning algorithm is going to search over. So remember, the learning procedure is essentially a searching procedure, right? So the search is guided by the labeled training data set of supervised learning, right? And then, of course, to conduct search, we need to specify the range of search. Right? So this range is actually called the hypothesis space. So this is a set of functions that the learning algorithm explores. Right? So, but be careful. Hypothesis space is not necessarily the same as concept space. So in complex applications, right? In many complex applications, so in fact, when people actually do not know what exactly the concept space is, or they just use a very general, very large concept space. But people usually, I mean, once you choose a learning algorithm, your hypothesis space is fixed, is there. Like if you're doing linear regression, right? That means your hypothesis space will be just linear functions, because you just estimate some linear functions, approximate target function. Right? If your hypothesis space is nonlinear function, like typically, for example, you're learning, you're training a deep neural nets, and then according to like universal approximation theorem, your hypothesis space can be like arbitrary, like continuous functions. Okay. Any questions so far?
Would the hypothesis space be considered a subset of the concept space?
Can you repeat again? What is hypothesis considered as what?
A subset of the concept space?
Um, um, it's actually you can consider the hypothesis space in that way, but usually people won't think about in that direction, because I want because I because ideally I want my search uh, procedure, right? This learning procedure can always identify some very close approximation to a target function. So usually we want the hypothesis space to be kind of superset of concept space rather than a subset. Like I want to use a highly flexible model like deep neural nets. I will know that deep neural nets can approximate arbitrarily continuous functions. And if you know that, okay, concept space the target functions will not be very, very complicated, then we feel safe to use larger hypothesis space.
Mhm. I'm not sure I quite get it. Do you have like a concrete example of a problem that machine learning is solving and like what the concept space for that is and what the hypothesis space for that is?
Yeah. So like, as I just said, like if you use machine learning, if you use linear regression, if you learn a linear regression model, so what is hypothesis space? The hypothesis space consists of all linear functions. But the concept space depends on the specific application. Like, um, like for weather condition prediction problem, right? So we have some reason to believe the concept plus, namely the type of target functions, are nonlinear. Meaning that now if you use linear regression model to estimate the target function in weather prediction problem, there can be some error because your hypothesis space is kind of like uh, mismatching the concept space. So that happens. That happens a lot in practice.
Is it useful to do that just to get a simpler answer, essentially?
Yeah, yeah, it is definitely useful, and I will discuss in depth later. So see that even meaning that taking a very large hypothesis is not always uh, the best. You see, a large hypothesis will easily lead to overfitting. And if you simple hypothesis, well, there must be some kind of gap, right, between the true function, target function, and the best approximation. Right? There always be some gap, but it can reduce some variances. So you see that there's kind of trade-off. It's not, meaning that it's not like as uh, as long as increase the size of hypothesis space, I can always improve my performance. It's not like that.
Mhm.
Does that
Yeah,
make sense?
I think that's good for now. Yeah, I think if you just keep going, I'll probably get it a little
Okay.
better.
Yeah, just to give you a sense, because this is a very basic concepts, and under that, based upon that, we can discuss more, more ideas and keep and uncover like more insights. So, any other idea regarding the understanding of those concepts, definitions? Okay, great. So, and training instances, right? So everybody is familiar with that. So more formally, you can write, you can describe, you can represent the training instances by a set of instances S, right? Cartesian product with -1, 1. It just means, okay, we have a list of pairs where each pair is a particular instance and the label. Remember, label is generated by the ground truth function f, right? So I have x1, the label of x1, x2, label of x2, xn, label of xn. Then these are the n training instances that are fed into the learning algorithm. So given the training instances, our learning algorithm, the goal of learning algorithm essentially is to find the hypothesis small h from the hypothesis space such that the prediction made by this hypothesis is the same as the prediction made by the target function. So obviously, in the training procedure, we can only we can only make efforts to ensure that these predictions are consistent across the training examples, right? But we kind of believe that if we can ensure the predictions made by the hypothesis are consistent with that made by the target function across the training examples, then our prediction is very likely to be consistent with the ground truth across the entire instance space. That's the whole like rationale of conducting supervised learning, right? By if we can well fit about a set of training examples, then we believe that our prediction will align with the prediction made by the ground truth in the future on same examples. That's the whole setup, the setup of supervised learning, right? So, and then how do we measure uh, if our learned hypothesis H can give the consistent prediction on the future on seen examples with the prediction made by the ground truth, right? So we have done that before, right? We just draw subsequent test examples from instance space, right? And then evaluate the prediction, right? So just to look at if our prediction is the same as the prediction made by the ground truth function, right? And uh, and uh, and and inside this setup, a key assumption is that the training instances and the test instances are generated by some fixed yet unknown probability distribution D over the instance space X. So this is a reasonable assumption, right? You can imagine that, okay, suppose my task is to do the image classification, right? I want to classify whether this image contains puppy, right, or some kind of dogs, right? And then during the training phase, I collect like 1,000 images, positive and negative instances, right, and train my model, right? And we assume, okay, those training images are independently sampled from some unknown distribution D over the instance space, right? Instance space right now is just the electrical images. Right? So obviously this distribution is very complicated. It's very likely that we even do not know its form, right? Probably it doesn't have any analytical form, right? But there does have some kind of distribution on that, right? And then during the test, we want to draw another set of test images from the same distribution, right? And we use that set of images to evaluate whether our learned hypothesis performs well. So, any questions so far? So those are all the necessary notations and setup regarding the things we're going to discuss in the next step. So hope everybody is on the same page. But those notations, I believe, is pretty straightforward, right? So now let us introduce the definition of the generalization error. Right? So previously, when we talk about like whether your learned hypothesis is good or not, how can we do that? We just sample a bunch of test examples, right, from some unknown data distribution D, right? And then we just evaluate the prediction accuracy, or in other words, the error on those test set. Right? If this test error is good, it is very small, we say, okay, it's good, right? Otherwise, we say, okay, your learned hypothesis is bad, right? But the problem with this test setting is that, remember, those test examples are random as well. Right? Maybe this time you collected like 100 test examples, and all the 100 test examples you give correct prediction, then your test error is 0. Like, can you conclude that, okay, my learned hypothesis is always good and always gives you a 100% accuracy? Obviously, the answer is no, right? Because you cannot guarantee that, okay, after another collection, like, let me draw another 100 test examples, right? Probably this time it gives you very bad prediction, right? And then your test error might increase to like 30%. But how can we address this problem?
Do test again and again, like do multiple tests and then average over the outputs, like sample sets from D, multiple sets, and then average over it.
Yeah, you're right. Yeah, very good. Yeah, very good point. Yeah, this is the most common use the trick when we evaluate our learning algorithm performance in practice. Namely, we either like we draw many test sets, right, and we test the performance of our learned hypothesis on each test set. We do the average, then we can give a much more robust estimate, right, evaluation of about the performance, right? Or we just collect a very large test set, right? Suppose I have collected 1 million test examples, right? So it is likely that okay, this 1 million examples kind of like will cover the whole instance space. So my my test error can be reliably evaluated. But again, I mean, although this is very robust in practice, but in theory, we want some kind of metric is not random, is invariant to the selection of the test set, right? Only given this invariant constant metric, we can do the further theoretical analysis, right? So that's why we're going to introduce this so-called generalization error. So what is generalization error? Given a data distribution D over the instance space, then we call the generalization error of a hypothesis H with respect to some particular target function f as the probability on the data distribution D that the prediction made by H is different from prediction made by f. That's it. So you can see this inequality, like hx is not equal to fx. This is a random event. Why? Because the test example x is random. It's sampled from some unknown data distribution D, right? So h of x is a function of random variable. So it's a random variable. F of x is function random variable. It is random variable. Right? So that means, okay, h of x is not equal to f of x is random even. So we define the generalization error as the probability that this random event happens. Does it make sense?
Yeah, I have a quick question about that.
Yeah.
So I know this is just standing as more of like a theoretical definition, but in practice, we don't know f of x. Like if we knew f of x, then we wouldn't even be writing this. We wouldn't even be doing machine learning, right? Because we know how this is mapped. So like, is there some like process then we can use to determine, like to approximate, like, I guess like how do you calculate this if you don't know what f of x is?
Yeah, that's a very good question. Yeah, you're right. So actually, this is just a theoretical definition. We'll never be able to exactly calculate this, right? Unless we want to do some theoretical analysis, like suppose we know the form of f, right? And we just want to analyze particular type of learning algorithm and how likely its generalization error will be, right? This is just this only has some theoretical value. It doesn't have like practical value. Or in other words,
Sure.
in practice, we just use that to give you concept, to give you idea.
Sure. Okay, that makes sense. Thank you.
And then we'll see like all kind of analysis is surrounding this definition, meaning that we want to estimate some or want to derive some upper bound of this generalization error.
Oh, sure. Okay.
Yeah, it's some theoretical things, but we need to give a clear definition. Otherwise, we cannot.
Yeah, it's a good point.
Derive some bound about this, right?
Right. Okay. Thank you.
Okay. Any other question regarding the definition? Okay, great. So to give a more concrete illustration, right? We can try to visualize, right? So suppose this is our instance space, right? So we have a target function f of f, right? So we can use this ellipsis or circle to represent the subset of instances which are labeled as positive by our target concept or target function f. So now suppose we use our learning algorithm to get a hypothesis H, right, which predict this set of instances as positive. So obviously there are kind of some gap, right? So now, where do we find the prediction error? We just look at the regions where the two functions disagree, right? So this part and this parts are the instances F and H disagree with the predictions, right? So these parts and these parts actually the where the H makes wrong predictions, right? So when we calculate the generalization error, we just calculate what is the probability of the instances here and what probability of the instance here. Okay. So in addition to the generalization error, right, as someone has raised the question, of course, the generalization error looks like it's not useful at all in practice, right? Because we'll never be able to calculate in practice, right? But in practice, what we concern most is another kind of error, is so-called empirical error. So what is empirical error? For target concept F, the empirical error of a hypothesis H is defined for a training set S as a fraction of examples X in S for which the function F and H disagree. That is, H of X is not equal to F of X. So to summarize, empirical error is just the training error. Actually, I haven't discussed about it in the last lecture, right? So basically, if you use H to predict the training examples, and you just calculate the fraction of the incorrectly predicted examples by H, that is the empirical error. So we denote by error SH the empirical error. Right? So now we have definitions of two errors. Right? One is generalization error. One is the empirical error. So generalization error is the measurement of the overall performance of your learned hypothesis. Right? So in predicting arbitrary example drawn from the instance space, right? And empirical error just measure how you perform in predicting training examples. Our rationale of conducting supervised learning is that, okay, if my empirical error is small, meaning that I can fit the training data well, I expect that my generalization error is small as well, meaning that it can generalize well to unseen future test examples. But now there's kind of like a catastrophe, right? It's called overfitting. So what is overfitting? A more formal definition is given here. So overfitting says when we have some empirical error on the training set is substantially lower than the generalization error, then we have encountered overfitting, which is definitely bad, right? Meaning that, okay, we're performing very, very well in predicting training examples, but when we generalize to unseen future examples, our performance drops substantially. So that's the more formal definition of overfitting. A normal case will be the normal behavior we expect, right? Will be like, okay, I get some pretty good empirical error, and then my generalization error is kind of approximately equivalent to the empirical error, or the same as the empirical error. But overfitting gives us a kind of abnormal situation, where, okay, you got like very small empirical error, but it's much smaller than the generalization error. Then that means bad. Usually that means, okay, your training set is corrupted by some noises, label noises, feature noises, whatever, and those noises lead to a bad hypothesis, which although this hypothesis fits the training data very well, but it gives bad prediction or wrong predictions for many new test examples. Okay. So now let us just arrange all the notations we have introduced so far, right? So we denote by X the instance space, namely all possible set of examples used for training a test, and label space by Y, right? So here we just consider like positive binary classification problem, so that we have two labels, positive 1, negative 1. And we assume, this is very important, we assume there is some kind of complicated but unknown distribution over the instance space X, right? So every time when we collect training or test examples, we actually join samples from D. And we assume that there is an unknown target function which maps from instance space to the output space. And this F is kind of instance from a concept class C. So remember the concept class examples we just given, right? Suppose given, for example, nonlinear functions, quadratic functions, sine functions, whatever, right? And also we have a hypothesis. Hypothesis is given by our learning algorithm, right? It's a hypothesis function which is also a mapping from the instance space X to the output space Y, right? So it is selected from learning algorithm from a hypothesis space, big H, and training set. So we have a training set, which we assume that it is a set of M training examples, and are independently joined from the data distribution D and labeled by the ground truth function F. And also we define two errors. One is called the true error or the generalization error, which is the probability that the prediction made by our hypothesis is different from the prediction made by the ground truth function F. And also we have an empirical error. This basically is the training error on the training set. So given those notations or given those definitions, there are a few like central questions the computational learning theory wants to answer. Right? So first question will be, can we describe a bound the generalization error given the empirical error? So you can see that. So in theory world, like we never do some like experiments. We never actually collect the test examples and then evaluate the prediction test example and calculate the error. We're not going to do that. We just assume, okay, we have evaluated the empirical error, right? They're giving all kinds of assumptions and conditions about model and data size, whatever, right? We want to estimate the generalization. In most cases, we just bound the generalization. What is the upper bound of the generalization error, right? How does this bound vary along with more training examples, or along with other conditions like confidence, like other things, as we will discuss later. And a second key question will be like, is the concept class C learnable, right? So what does it mean for learnable? And so we need to first define the definition of learnable. Right? But intuitively, here learnable is related to feasible, right? Feasibility, right? If I say, okay, I can spend like 10,000 years to learn this particular target function, well, it shouldn't be called learnable because it's not feasible, learnable. And the third question is, how many examples does an example need to guarantee some good performance? This is also referred to sample complexity. Meaning that, okay, if I want my learning algorithm to give like 0.01 generalization error, how many training examples at least we should collect? Right? So obviously, if a learning algorithm does not need too many training examples to achieve the designated error level, then that learning algorithm is really good, right? Because we do not, we reduce a lot of cost of collecting training examples. And third question is how much cost does an algorithm take to learn a class C, right? This is related to computer science, right? So this is related to computational complexity, right? If you're that is basically about like how efficient your searching procedure, right? If your searching procedure is kind of like NP hard, then it is not practically useful at all. Like we discussed before, like if you want to learn a minimum decision tree from data, right? If you do the combinatorial search, well, the searching procedure is too costly, right? This is not practical. That's why we resort to a greedy heuristics. Right? So to answer those questions, we need to set a kind of a reasonable expectation about the learning performance. So here comes a very important idea in computational learning theory. So first, we need to be realistic. We cannot expect a learner to learn a concept exactly. Meaning that I can exactly recover the underlying target function. This is usually infeasible and is not valuable to discuss about point because it's so hard. Right? Nearly no practical learning algorithm can achieve that. So why we can view this, we can see this point in several aspects. First, because the training set is always finite, right? It's limited. So in general, there can be multiple concepts or target functions consistent with available data, meaning that from the beginning, the learning algorithm, no matter how powerful it is, it will never be able to recover exactly the original concept, right? Because there could be concept one, concept two, concept three. Both three can perfectly give exactly the same labels on this set of training examples, right? That means, okay, you'll never be able to identify which concept is the true concept given this confusing subset of training examples. Right? And secondly, so unseen example could potentially have any label. So we expect that, I mean, the learning is like that, right? We expect that, okay, after we have trained our algorithm or train our model with the training examples, right? Then for unseen examples, the closer the test example or test inputs to the training inputs, the more likely they have like similar labels, right? But this is kind of like on average expectation. In practice, due to the randomness of the data, right? So there is no guarantee on that. You cannot cover all possible cases. You can only say, okay, with a large chance, they have this kind of label. There's no such kind of guarantee. And also, again, due to the limit size of training set, we agree to misclassify some uncommon examples. Like for some uncommon examples, they're not show up in the training set, then it is easy to make mistakes. This is the first point, right? So we cannot expect a learner to learn a target function exactly. But then, can we step back a little bit, like, can we expect that we can always learn a function which is close to the target function? Meaning that, okay, can we guarantee that we have some learning algorithm can always find a close approximation to a target concept? Can we? Any thought? Any suggestion? Any optimistic opinion, or not that optimistic opinion?
So you're asking if we should expect that we can create a learning algorithm to make a close approximation to any target function?
Yes.
I would probably say no,
Why?
because I think that's, even if we could design one, it would be difficult to prove that it could make a close approximation for a significantly difficult problem. And I think um, I think that you can probably essentially just keep making the problem more and more complex infinitely, right? If that makes sense.
Yeah, that's one way to think about that. So, but actually, we can also construct a more and more complex hypothesis space, like as we just mentioned, right? Like if you use deep neural nets, according to some universal approximation theorem, deep neural nets can approximate arbitrary complex functions as long as that function satisfies some continuity assumption.
Okay. What do you mean by close approximation then? Like
Close
how?
approximation just means okay, their norm, like difference norm, is smaller than arbitrary threshold, or uh, more roughly speaking, you can consider like if I can sample a great many of inputs, right, and difference, the difference between their predictions or the function values are smaller, can be smaller than arbitrary designated value.
The approximation to our target concept will depend on probably what kind of training data we have, right? Like
Mhm.
if our training data is not representative of the instance space, then we might not get a close approximation at all, like the one that we just said above, that uh, it might not be, the data might not be spread to the whole distribution. It might come only at random samples. It might cluster.
Yes, exactly. Yeah, that's exactly the point I want. Yeah. So basically, it is determined by the data as well, right? It's not only determined by how expressive your learning model or the hypothesis space, right? So as we discussed, right, we have like people are really smart, researchers are really smart. We can design all kinds of like expressive, complex space such that okay, we can optimistically assume okay, we can cover any possible target function. But another deterministic factor is the training data. So even if you have a very powerful model, right, if your training data is of low quality, you cannot guarantee to get a good approximation to the target concept as well, right? So because the learned hypothesis can be some way is essentially determined by the training data, but the training data are random in nature, right? Remember, the training data are sampled from the data distribution D, right? So uh, we can imagine that, okay, in one case, my training data might be very good, right? Well spread over the instance space, well summarized instance space, so that using that data, I can find a hypothesis which is really closely approximate to uh, which is really close to the target function, right? But if we draw another set of training examples, right, but this time we have a bad lag, such that okay, our training data for concentrated on a very small region of the instance space, right? And then if you use that for training, then your hypothesis might be much worse. So that means we can we can either we cannot always we can also not we cannot always expect to learn a close approximation to our target concept. It comes out some randomness as well because of the training data. So you can see the condition or the expectation in computational learning theory about a good learner is kind of like quite restrictive. So we cannot expect a learner to find the exact concept. Right? We can expect that we can always find a good approximation. So then what about the remaining guarantees we want to seek for? We now go back, we now step back, right? We can only seek for a high chance to find a good approximation. So because these two conditions are not realistic, because the hardness, the finite size of training data, right? And also because of the training data set itself is random, right? It can vary across different collecting procedure, right? So now, if we want to give a realistic expectation for a good learner, then we need to introduce some kind of probability level. So we see that a good learner will have a high chance or high probability to learn a close approximation to the target function. That's why you see, like in computational learning theory, there are always some kind of probabilistic statement, probabilistic conclusion, like with high chance, it has the generalization error is bounded by blah blah blah, because it's not realistic. It cannot give you always guarantee. Okay, and then we're going to talk about this very important concept called probably, approximately correctness. But from our discussion, right, we have just discussed, right, we kind of get the key meaning, right, the key idea why this so-called probably approximate correctness come out, right? Because we have to introduce some kind of probability. So probability approximate correctness actually gives a criterion to differentiate those good learning algorithm and bad learning algorithm. So what do we mean by good learning algorithm? So we really will those learning algorithms which satisfy the probably approximate correct learning as good learning algorithm. So let's see what's the definition, right? So to talk about this pack learning, right, probably approximate correct learning, we need to first give some parameters. So first, we need to give small parameters epsilon and delta. So as we'll say, epsilon actually indicates the level of the generalization error, and delta actually indicates the probability level. So as that refers to what we have discussed with high chance, high probability here. And also, it requires our learner, right? If our learner satisfy the probably approximate correctness, and it requires our learner with probability at least 1 minus delta produces the hypothesis with true error at most epsilon. So you can see this is kind of quantify this definition, right? So we want our learner to have high chance. So how high the chance with probability at least 1 minus delta, and how close to the target function, the true error at most epsilon. Does it make sense?
I think your slides are frozen.
No, I haven't moved it.
Okay. It's just in the chat, someone said that they were on the last slide, the requirements of learning slide.
Oh, really?
Yeah.
Oh, let me. So can everybody see the slide moving? I'm transitioning.
I'm on the PAC slide myself.
How
It
about
hasn't
now?
moved.
It's moved.
No.
Okay.
No.
Yeah, I'm just stopping for a little more time to explaining those notations, because this is kind of like lengthy and tedious, but I want to make sure everybody is on the same page. Okay. So so now let us introduce. Oh, by the way, so the basis that we can expect that, like with high chance we learn a close approximation to the target concept, is assumption that we assume the training data and test data come from the same underlying data distribution D, right? We'll realize this point in more depth as we proceed. So now we give the definition of pack learnability. So we consider a concept class C, namely a type of the or family of target functions. And these target functions are over an instance space X, and well, the dimension of the instance space is n, meaning it's, all the instances are like n-dimensional feature vectors, right? And also we consider a learner L, which search over a hypothesis space big H. And then pack learnability says that, okay, if the concept class C, meaning all the target functions C, is pack learnable by our learning algorithm L using H, if the following conditions are satisfied. For every target function in C, and for every possible data distribution over the instance space, and for every fixed epsilon delta. Suppose we want to use M training examples, which are sampled independently according to D, to train the algorithm L. And the algorithm L guarantees to have a probability at least 1 minus delta to find a hypothesis, small h, that has the generalization error at most epsilon. Then this M must be polynomial in 1 over epsilon, 1 over delta, n, the dimension of the feature vectors, and the size of the hypothesis space. This looks really lengthy definition, right? So never mind. So don't worry about it. Let us read it again, right, to fully understand the definition. So we say the concept class C, namely this family of target functions, are pack learnable by our particular learning algorithm L using the hypothesis space H, if for any function in C, any data distribution, any error level and confidence level, we only use a polynomial number of examples in these 4 numbers. The algorithm L can have high chance, meaning 1 minus delta, produces a hypothesis whose true error is at most epsilon. Does it sound more reasonable?
Can you say what epsilon and delta are again?
Yeah, epsilon means the error level, right? And delta means how likely, how high the probability you give this high quality hypothesis. So here, epsilon indicates the generalization level, and delta indicates the confidence level. So recall that our error, or the generalization error, is defined as the probability that your prediction made by hypothesis is inconsistent with the prediction given by the ground truth function, right? So basically, pack learnability says, okay, for all possible choices of the target function, data distribution, error level, and confidence level, as long as you have a polynomial number of training examples to this 4, right, then our learning algorithm is good enough to give you a very good hypothesis with high chance. So how good is hypothesis? The error is at most epsilon, right? And how high the chance? At least 1 minus delta. Does it make sense? yeah, it's kind of lengthy, tedious, because to rigorously define this, you have to you have to take some kind of space, some paragraphs to illustrate. But the idea is there. Like, so basically means that okay, if my algorithm L is good, like, it's good meaning that I can pack learn this set of or this type of target functions. Then what criterion I should satisfy? Right? I should be able to well learn arbitrary function in this concept class under arbitrary data distribution in the instance space on the arbitrary designated error level on confidence level. As long as giving me a polynomial numbers to this polynomial numbers of training examples to these four numbers, I can have a high probability to give you a good hypothesis, meaning how high the probability is, at least from the start. How good the hypothesis, the error is at most epsilon, or upper bounded by epsilon. So is everybody good with that?
I think I get the general concept. I don't quite understand that last line. So like, you know, it's setting an expectation on how many training examples from D that we have. But I don't recognize the language of saying where n is polynomial in, and then you give these different values.
Okay, so this is a term from the so you get a key concept, right? But you just feel a little bit like odd to say polynomial in this, right?
Yeah.
Okay, yeah, that's very good. So polynomial in just means you can view m is a polynomial function of these four numbers. So again, so if we increase the dimension n, or increase 1 over epsilon, or increase 1 over delta, so m, the growth of m is polynomial to their increase. This is a very commonly used metric in describing the algorithm complexity or symptotic complexity when growing with the the input.
Yeah, that makes sense. Okay.
Yeah.
So but we have four inputs. So like any and all of those can affect essentially the bound.
Yes, of course.
In a polynomial fashion only, though, right?
Yes.
Okay.
Exactly. Yeah.
Is that strictly polynomial, or can it be lower or higher than polynomial? Like, which way are we restricting this?
Is lower than some polynomial.
Okay.
Yeah. If it's higher than, then this there's no meaning for us to discuss about that. For example, if it's higher than polynomial, now it means if it is exponential, that's not what we want. So in computer science, polynomial is always a good thing, meaning that okay, it is scalable, it is feasible. If it is saying okay, it is exponential to this kind of thing, it just means okay, well, in practical, it is not practical.
Okay.
Yeah. So like in many algorithm design, right? When we say okay, we can solve this problem in polynomial time complexity to the the problem scale n, or data size scale n, that is very good, meaning that okay, you can implement in practice. But if you say okay, it's exponential to that, you can imagine when your problem scale grows, then the cost grows like exponentially. It's too fast. Okay, so so this is definition of pack learnability. So it's basically talk about what kind of requirement of the size of training examples to achieve this good performance. So we can give a further definition about the pack learnability. So we say the concept class C is efficiently learnable if our algorithm L can produce the hypothesis in time that is polynomial to these four numbers as well. So basically it covers another point, that's computational efficiency. So the original definition of pack learnability is just talking about okay, how many training examples do you want? Right? We want that okay, it is polynomial to these four numbers. And then efficiently pack learnable mean that okay, not only we do not need not only we just need a polynomial number of training examples, but time complexity is also polynomial to these 4 numbers. So this 4 number actually represents the skew of the problem, of the learning problem. So any questions so far? Yeah, so if you feel like still feel uncomfortable in this, so just after class, I'll suggest you to read through this definition for like 5 times. You'll get used to that, because in computational learning theory, you will see such kind of statements everywhere. Okay, so what kind of insights can we extract from this definition? Right? So actually impose 2 requirements for a learning algorithm to satisfy the pack learnability. So first, we want polynomial sample complexity. So this is actually about some information theoretical constraint, meaning that we do not need too many training examples to ensure our learning algorithm to find a good hypothesis with a high chance. That's okay, because in machine learning applications, like the computational efficiency of learning algorithm itself is important for sure, right? But another important aspect is the cost of collecting training examples. Right? In many applications, collecting those training examples can be costly as well, right? We actually do not want to collect like trillions of training examples to have our model to learn very well. We want to minimize our cost of collecting training examples. That's why we define a good learner to only require a polynomial sample complexity. A second thing is about computational efficiency, right? That's where the efficient pack learnability requires, right? We want polynomial time complexity. Right? So the computational complexity. So we can see that pack learnable is kind of like very strong requirement, right? Very, very strong conditions which our learning algorithm should satisfy, right? So we require that for arbitrary epsilon delta you're choosing, our learning algorithm, as long as given a polynomial number of training examples, we can find hypothesis with high chance whose error is upper bounded by this epsilon. So epsilon can be arbitrarily small. So basically means that this basically implies that your hypothesis space must be enough large. Given arbitrary epsilon can be 0.1, 0.01, 0.0001. Right? So given arbitrary epsilon, as long as we give enough polynomial number of training examples, we always guarantee our hypothesis has high chance to find a close enough, our learning algorithm has high chance to find a close enough hypothesis whose generalization error is upper bounded by this arbitrary small epsilon. So that basically means your big H's must be large enough. Right? And usually, in theory, we assume the hypothesis space is a superset of the concept space. It's very large. And also, if H happens to be the same as C, then we call our learning algorithm is kind of properly pack learnable. But this is just the definition of some term. So you can see the pack learnability is essentially a worst case definition. Right? Why? Because if we conclude a learning algorithm can pack learn some concept plus, right? Then the algorithm must meet its accuracy, right? For every distribution on the instance space. Right? So this is essentially a distribution-free assumption. And for every target function f in class C. Right? So this is not like on average, we require even the hardest concept class C, we can meet the accuracy with high chance. So any question regarding the definition of pack learnability?
So if you're writing a computer science paper, or if you are a company trying to sell your machine learning product, say, something that you promise will be able to learn things well, this definition seems like too rigid, or unreasonable to have like an unreasonably high or specific standard for claiming, hey, like this machine algorithm learns well, right? Because, and you'd even have to clarify that with like, it learns well with this amount of confidence level, right? You have to kind of clarify with a lot of things. And you definitely can't test every distribution, nor can you test every target function. You have to say like, we tested this many target functions and this many distributions, right, across the space. Does that?
Yeah, yeah, you're definitely right. I totally agree. Yeah. So of course, pack learnability is not appropriate to use to sell your developer learning algorithm or software. It's not. It's just a theoretical criterion that used to analyze the different test algorithm. But even as a theoretical criterion is really strong. I agree. I totally agree. So based upon Parker learnability, there are other definitions or variants on that, which can give a weak definition of Parker learnability, like weak Parker learnability, whatever. It's not. I mean, this is not the only criterion that we use to examine, in theory, the performance of different learning algorithms. There are many others, but here I just, because this is so fundamental, is important in theoretical analysis. So I bring it up and let everybody know. But even in the computational learning theory, the research, people are not always focused on pack learnability. They might like turn to more practical definition about learnability.
As an extension to that, for the project, the non-competitive project, what kind of metrics will we be striving for, or like trying to illustrate?
Oh, you don't need to use pack learnability unless you want to do some theoretical project.
Just what's kind of coming down the pipe in terms of that? What should we be thinking about?
Well, the most commonly used metric is still the metric you use in your homework, like mean square error, like area under curve, or classification accuracy. We don't require you to give theoretical guarantee that your device algorithm can pack learn anything. No, you just show on like a decent number of training test set, your algorithm is working well. That's enough. Like you cannot say, okay, on 10 test examples, my prediction accuracy is 100%. Well, that's not decent. That's not. But at least you have collected a bunch of test examples, like 100, 1,000, and show, okay, it is working well. That is okay. But I just want everybody to know that even you can give some kind of like reliable estimate of the generalization error, right? The test error used in practice. But there is some kind of conceptual definition about generalization error, which is invariant, which is non-random, which truly reflect the performance of your learned model.
Very cool. Yeah, absolutely. Thank you.
Okay, great. So yeah, on Thursday, we're gonna use this simple and naive framework to mathematically justify Occam's research principle. This will like largely deepen our understanding of this principle. Okay, see you on Thursday. Yeah, thanks.